Okay. So when Francis, as I told, he came to me with this problem. He did not come to me with the approach me with it as a problem in domination theory or on total dominating set. He came to me with a problem, a coloring problem, okay, called the coupon coloring. I know this is a graph theory audience, so some of the introductions that I do may be already very much familiar to you, but still, for the sake of completion, let me start with the coloring that all of us know, which is the proper coloring. This is a coloring of the vertices of a graph so that no two adjacent vertices get the same color. This is the familiar notion of a proper coloring. And the coupon coloring is quite a different kind of coloring of the vertices of a graph. It is still a coloring of the vertices of the graph, but now the condition is that if you take any vertex, say you are using some k number of colors, if you take any vertex and look at its open neighborhood, okay, so open neighborhood is all the vertices which are attached to it, but not counting the vertex itself. So the open neighborhood should contain a representative of each color, at least one representative or one vertex with each color. So in some sense, every vertex wants to see all the colors that are used in its open neighborhood. Okay, so that's the definition of what a coupon coloring is. The picture, the C4 shown on the right side here is an example of a coupon coloring. Okay, so for example, you can see that the vertex numbered 1. Here we are using two colors, the red and blue, and the vertex numbered 1 sees both blue and red in its neighborhood. One point that I want you to take note of is that one is happy, one sees when I say one sees a red, I mean the red that is on 2. The red that is already on 1 doesn't count because that's not the open neighborhood. Okay, so this is the idea of coupon coloring. Okay, and the picture that you see here is one example. So in particular, please keep in mind that a coupon coloring will never be a proper coloring, because every vertex, let us say it is of some color I, it has to see at least one other vertex of color I in its open neighborhood, which is a direct violation of the requirement of a proper coloring. So in that sense, coupon coloring would never be a proper coloring. Okay. Now, what we just saw, this definition is what I generally like to call as the local view of any coloring. Okay, this is what I generally call as the local view of a coloring, where you talk about some property that a vertex or an edge or the neighborhood of a vertex has to satisfy. Any coloring also gives what I call as a global view. Okay, so in a global view, any vertex coloring can be treated as a partition of the vertex set of the graph. Okay, these partitions are nothing but the color classes, or every part in the partition is the set of vertices which have the same color. We would all know that this forms an equivalence relation. Hence, the parts that we are talking about are nothing but the equivalence classes of this equivalence relation. Okay, what all of us call as color classes. Okay, so given any coloring, the global view is about asking what do these color classes form. Okay, as an example, if you take a color class of a proper coloring, then each color class turns out to be the familiar notion of an independent set, a set in which there is no edge between two vertices in that set. Okay, no, a set which does not contain any edges between them. So, and hence proper coloring is nothing but a partition of the entire vertex set of the graph into parts, each part being an independent set. In that context, on a similar line, we should ask the question as, what does color classes in a coupon coloring represent? Okay, so what does each color class, so given a coupon coloring of a graph, what does each color class represent? Okay, I'll be happy if somebody answers from the audience, but since I really do not know about the format of this talk, I'll maybe wait for a second and continue. Okay, so if you think about it, the demand that coupon coloring keeps is that every vertex should see every color in its neighborhood. Now, if you invert that, that means every vertex is dominated by, or every vertex is adjacent to at least one vertex of each color. Okay, so you take any color class, let's say that all the red vertices in your coloring. Every vertex in your graph has a red neighbor. That means that vertex is dominated, and this is true even for the red vertices. And hence, this is in fact a total domination, not just a domination, right? I mean, in this workshop, we have already seen these notions of domination and total domination multiple times. So I do not have to elaborate further probably, but please feel free to ask me if the following, because this is one of the key claims that I'm making. In a coupon coloring, each color class turns out to be a dominating set, and therefore a coupon coloring on the whole is a partitioning of the vertex set of a graph into different total dominating sets. Okay, I hope it is clear, but feel free to ask if something is not clear. Okay, now this slide is probably an overkill for this workshop, but let me just remind the definitions. You know, an independent set is a set in which no two vertices are adjacent. A dominating set, a set S is called dominating if every vertex outside of that set is adjacent to some vertex within the set. And a total dominating set is a set such that every vertex, not just those outside, including the vertices in S, is adjacent to some vertex in S. So if you look at the picture on the middle, the vertices 1 and 3 colored in blue, they form a dominating set, but not a total dominating set, because vertices 1, for example, vertex 1 doesn't have a edge to a blue vertex. Okay, whereas the rightmost picture where you have this 1 and 2, this is in fact the red vertices form a total dominating set. Okay, now what are the non-trivial questions that one can ask here? If you are talking about independent set, then surely empty set is an independent set, singleton sets are always independent. So the natural question is, what is the largest independent set? In fact, the size of a largest independent set is called the stability number of a graph, and it is usually denoted as alpha of the graph. Whereas when it comes to dominating set or total dominating set, what is interesting is to find the smallest dominating set or a total dominating set. Again, the largest here is not interesting because the whole vertex set, if you take, that is easily, unless you have isolated vertices, it is easily seen to be a total dominating set and a dominating set. Okay. So the size of the smallest dominating set is usually denoted by gamma of G, called the domination number. Size of the total dominating set is denoted by gamma T of G, called the total domination number, and so. But now when you think about the coloring equivalent or the coloring way of viewing it, which is about partitioning the vertex set into different parts where each part is a set of our type. In the case of independent set, the interesting question or the non-trivial question is to minimize the number of independent sets. Okay, this is the classic chromatic number question. The minimum number of independent sets into which you can partition a graph is the chromatic number of that graph, denoted by chi of G. Whereas when it comes to partitioning into dominating sets or total dominating sets, the natural question is the maximum number of parts. So in the coloring language, we are trying to give maximum number of colors so that each color class is a dominating set, or in the last one, each color class is a total dominating set. Okay, these parameters are respectively called as the domatic number and the total domatic number. And the total domatic number is usually denoted as dt of G. But by the discussion that we had so far, it should be clear that this number is nothing but the coupon coloring number. Okay, what was the I did not formally define what is a coupon coloring number. It is again the maximum number of colors you can use in a coupon coloring of the given graph. Now, since every color class has to be a total dominating set, this splits the graph into this partitions a vertex set into total dominating sets, and hence this number turns out to be equal to the total domatic number. Okay. So I'll use this both models during the proof that I'm giving. I might present the proof mostly as a coloring argument. Okay, though the result I have stated in the language of having a partitioning of planar graphs, planar triangulations vertex set into total dominating sets. Okay, now coming to the graph class of our interest, we are going to study mainly plane triangulations, which are planar graphs, or rather the graphs already embedded on the plane, which we call the plane graphs, with the restriction that every face is a triangle. Okay, so we all know that these are equivalent to saying that you add as many edges as possible without violating planarity, or so-called maximal planar graphs. In the paper, we have a result that applies in a slight more generality. We work on a graph class called near-triangulations, but for the purpose of this talk, we will restrict to planar triangulations. Okay, so every face is a triangle. Okay, what do we already know about these parameters, alpha, gamma t, etc. of plane triangulations? Let's assume that n is the number of, whenever I write n in this slide, n represents the number of vertices in the graph. The famous four-color theorem says that any planar triangulation, any planar graph, and hence a planar triangulation in particular, can be properly colored using 4 colors. So that's a partitioning. It says that any planar graphs vertex set can be partitioned into 4 independent sets. Hence, if you take the largest among the 4, you would get an independent size of size at least n by 4, and this gives a lower bound on alpha. Okay, this is one of the most famous results in graph theory. On a similar line, Matheson and Tarjan in 1996 showed that in any planar triangulation, in any plane triangulation, you can find, or you can partition a plane triangulation into 3 dominating sets, right? That is, they showed that the domatic number d of g of any planar triangulation is at least 3. This again, since these 3 parts are, each part is a dominating set, if you take the smallest among these 3 parts, its size is going to be at most n by 3, and using it's going to be at most n by 3, and using this idea, Matheson and Tarjan concluded that the domatic number of a plane triangulation, gamma g, is, sorry, the domination number of a plane triangulation, gamma g, is at most n by 3, by taking the smaller among the 3 color classes, right? This, and they also conjectured that except for some examples, counter examples like octahedron and so on, actually this gamma g could be upper bounded by n by 4 instead of n by 3. Okay, but this conjecture is open. It was proposed in 1996, like what, 27 years ago. It is still open. There was an improvement from n by 3 to something like 17 n by 53. This was in 2020 by Spakapan. And it seems there is a recent improvement which improves it further, but still doesn't reach n by 4. Okay? But that paper is currently only in archive. In the context of total dominating, the problem of total dominating sets, it's known that any plane triangulation has a total dominating set of size at most 2n by 5, with a couple of exceptions. This is a result from 2020 by Claverol, and there was a conjecture when we started working. There was a conjecture that the domatic number of any planar triangulation is at least 2. What does that mean? In fact, any planar triangulation other than the triangle. Okay, so it means that either we can think of it as every plane triangulation has a coupon coloring using 2 colors, or we can also state it as every planar triangulation can be partitioned into 2 parts such that each part is a total dominating set. Okay, and that is our key result. This was published last year in Journal of Graph Theory. The result was originally conjectured by Goddard and Henning in 2017. Okay, again, when I state this result, a triangle is an obvious exception. That is why we have the condition that n is greater than or equal to 4. Okay, so this is the result that we are planning to present in this talk. Okay. So yeah, maybe I think I will skip the recap. I have already, but the only thing that the reason why this slide is that, I mean, we should now I will be talking more in terms of a coupon coloring. Remember the definition of coupon coloring: every vertex sees every color in its open neighborhood. Okay, it's not enough. Even the color that is on that vertex itself has to be seen on some other vertex in its open neighborhood. Okay, so what we will actually end up now in the proof, we will present the whole proof in the language of coupon coloring. So we will show that any planar triangulation, we can give a coloring such that we can give a two coloring such that every vertex sees both the colors in its open neighborhood. Okay, that is how the proofs will be presented. That is why I wanted to have this slide as a recap. Okay, again, it's a good time for questions if any of the definitions or terminology is not clear. Okay, if not, let us begin. Okay, so the K4 that you see here, the coloring that is given to it is already coupon coloring. You can verify that each, the coloring uses only two colors, red and green. You can verify that each of the four vertices, any of the four vertices you take, it will see both red and green in its open neighborhood. Okay, the icosahedron that you see here, right? You can verify with, if given some time, you can easily verify that this is also a coupon coloring. We have used two colors, and you can verify that every vertex is both red and green in its open neighborhood, right? But let us say you try to give a coupon coloring using two colors to the 6 cycle that you see here, right? We will see that it is impossible to do. Okay, say for example, without loss of generality, I can give this vertex a red. Now every vertex should see both a red and a green in its neighborhood. So again, without loss of generality, this vertex let me call 1, that sees a red and a green in its neighborhood. Okay, now this vertex 2 has already seen a red in its open neighborhood, the vertex 1. So it needs a green, which means this vertex 3 has to be a green. Okay, now vertex 3 has already seen a green, sorry, the vertex 3 has already seen a red in its neighborhood, in its open neighborhood, which is the vertex 2. So in the other neighbor, it has to see a green. Okay, remember the green on itself doesn't count. It has already seen a red, so it has to see another green. Okay, but now look at the vertex number 4. It has seen a red, sorry, it has seen a green at 3, which means the vertex 5 has to be a red, so that 4 sees both the colors. But now you already see a conflict, right? This vertex 5 is not happy because in its open neighborhood, both the vertices 6 and 4 happen to be of color green. Similarly, if you see the vertex 6 is also unhappy because both the colors on its open neighborhood are red. Okay, so the 6 cycle cannot be two coupon colored. For this, you will need at least you can at most coupon color it using one color. Okay? By the way, once the graph doesn't have a isolated vertex, if you give every vertex the same color, it is a one coupon coloring. So that's a trivial instance. Okay, so the 6 cycle only has a trivial coupon coloring, nothing better. Similarly, you can verify that in a triangle also. However, we try to color it using two colors, you will see that this vertex is unhappy because both of its neighbors happen to be red. So this is one exception to the result that we are talking about. Our result is only for triangulations other than the triangle alone. Okay, if you take the triangle alone, it doesn't have a coupon coloring using two colors. Here the coupon chromatic number is at most 1. But other than the triangle, we will show that every other triangulation has a two coupon color. Okay, now the warm-up continued just to see that we are familiar with this idea of coupon coloring. Coupon coloring of any graph is at least one, provided it has no isolated vertices. Color everybody with the same color. Everybody has a neighbor, and that neighbor has the color. So one coupon coloring is easy. Whereas checking whether a graph has a coupon coloring using two colors or more is already NP complete. Okay, so once the only trivial instance is coupon coloring equal to 1, unlike the proper coloring, right? In a proper coloring, even 2 coloring is easy. It's equivalent to whether checking whether the graph is bipartite. Now, a very easy upper bound is that coupon coloring number is upper bounded by the minimum degree in a graph. Look at the vertex with the minimum degree. In its neighborhood, there are at most little delta many vertices, and hence you can see at most little delta many colors. So the whole coloring, since the demand is that every color appears in the neighborhood of every vertex, the maximum number of colors you can use is also little delta. Okay, and for the cycles, you can verify this given time. We saw that the 4 cycle can be colored using 2 coupon colors, and it turns out that if the length of the cycle is 0 modulo 4, you can always do 2 coupon coloring. Otherwise, you can do only a 1 coupon color. Okay, and for the complete graph, you like on Kn, you can have a coupon coloring using n by 2 colors, floor of n by 2 colors. You essentially have to give the same color to at least 2 vertices so that they see each other, and that will work. Okay. So now let us, before we give our proof, there were previous attempts at solving this problem. Okay, the problem was posed in 2017, or the conjecture that any planar triangulation other than the triangle has a 2 coupon coloring was posed in 2017. There were a couple of attempts, or in fact 3 or 4 attempts before our result, and we have used some of the ideas that were discovered during these earlier attempts. Okay, so we are presenting some of them as special cases here. Okay, suppose all the degree in the given planar triangulation. So our G is going to be a planar triangulation, not an arbitrary graph. Now, suppose all the degrees were an odd number. Okay, then it is very easy to get a 2 coupon coloring. What do? We use the 4 color theorem. We use the big machinery of the 4 color theorem. We do a proper 4 coloring. Okay, the classical proper 4 coloring of the graph, say using colors blue, brown, green, and gold. Okay, just pick 4 color names. And what I do is I now merge these 4 colors into just 2. Okay, say blue as well as brown, I just call it B. Okay, and which means any vertex that is colored blue or brown will be merged into a single color called B. Similarly, any vertex which is either colored green or gold, so the green color class and the gold color class together will form the color class G. Okay, so this is a color merger argument. A very simple thing, right? I mean, originally the 4 coloring is a partitioning into 4 parts. This makes this into merges 2 of these partitions, so that finally we have a partition into 2 parts. Okay, this color merger we will use throughout this talk. Okay, so but in this very special case, this B and G actually form a 2 coupon coloring. Okay, why is that? Because look at any vertex. Okay, we will have to argue that the neighborhood of the open neighborhood of that vertex. Now, since that vertex is since our graph is a plane triangulation, the neighborhood of any vertex, looks like a cycle, right? Neighborhood of any vertex is a cycle, and since the degree for every vertex is odd, the cycle is also going to guaranteed to be an odd length cycle. Okay, now in an odd length cycle, any proper coloring will give 3 colors. Okay, not 2. It has to use at least 3 colors, either 3that appeared in the cycle, then you will surely get a B and you will surely get a G. So this problem, if the planar triangulation is such that every vertex degree is odd. Okay, there are no colors or there are no bichromatic cycles, no cycles which use only two colors. Okay. Now, this not every planar graph is acyclic four colorable, but a very large subclass of planar graphs is acyclic. Same, because you look at the neighborhood of any vertex, that is a cycle. This time it needn't be an odd cycle, it could be an even cycle or an odd cycle. But since the acyclic restriction ensures that this cycle is not bichromatic, it sees at least three of the original colors, and hence after merging, it sees both of the merged colors. Okay, so every vertex is happy, it sees both the merged colors in its neighborhood, so you have a two coupon color. This result can further be extended to what are known as acyclic 2-2 colorable graphs, but I'll skip that in the interest of time. Okay, but this technique of color merging is something which we will use again. Okay, now, by the way, this result was already in the paper by Goddard and Henning, which introduced the conjecture. Now, a later paper by Gabor also settled the conjecture if the minimum degree of the triangulation of G was at least 5. Okay. Now, they had a very different approach, and we also use this approach in our proof. In fact, we consider our proof as an extension of the technique by technique in this paper. Okay. So suppose your planar triangulation has a minimum degree 5. Now, the first step in the proof is to find a cut, okay, or a split the vertices of the planar graph into two parts. Oh, am I audible now?
Okay. Deepak, okay, I think you disconnected, huh? Okay.
Yes. I had an internet outage here. I hope I'm audible now.
Okay, yes.
Okay.
Okay, everything okay.
Thank you.
Continue, please.
Thank you. So sorry for the interruption. Okay. So yeah, so I was talking about how earlier paper by Hanna Gabor solved the conjecture when the minimum degree of the graph is 5. You start with a max cut in your planar graph. So this is a bipartition of the graph so that the maximum number of edges cross the cut. And it is an easy observation that if you take such a cut, for any vertex, at least half of its edges incident to it cross this partition. It's easy to prove this because suppose you have a vertex such that there are more edges into the same part than to the other part, then what you can do is you just shift the location of this vertex from its current part to the other part. You will increase the number of edges that are crossing the part. So, which means there's a contradiction. The original partitioning was not a max cut. So, if you take a max cut, then for any vertex that you see here, any vertex on a side, more number of edges will go across the partition than into the same partition. Okay. So now since your minimum degree is 5, half of 5 is 2.5. So at least 3 edges will go to the opposite side. Okay. So the number of edges that are going to the opposite side is what I denote by this delta cross for crossing. Okay. So the minimum crossing degree, like every vertex will see at least 3 neighbors on the other part. Okay. We are going to make use of this observation very crucially. Okay. Now we do some tweaking of this graph. Okay. Or Gabor et al. In their paper does some tweaking of this graph. Say they delete all the edges within the green part. Okay, so the first part, the green part, every edge which is within that is deleted. So the green now becomes an independent set. And we know that every green vertex, the vertex, no, by the way, this green and red will have nothing to do with the final coupon coloring. I'm just saying green and red so that I can point instead of saying left and right, or maybe I'll say left and right. So every left vertex here will have at least 3 neighbors on the right. Now, if it has more than 3, we delete these extra vertices and extra edges, sorry, not extra vertices. We delete these extra edges and make it exactly 3. Okay. That way we end up having every green vertex sending exactly 3 edges to the right side, Okay. This is the pruning that we do. Now let us imagine this graph in the planar drawing fashion. Okay. In order to visualize the cut, we kind of use the classic view of, the way we view a typical bipartite graph. Let us go back to the planar view. Okay. But after all these deletions have been done, which means any edge that was between two left vertices was deleted. And if a left vertex had more than 3 edges to the right, only 3 of them was retained. Now, after you do all of that, we look at the same graph in a planar fashion, and now look at the neighbors of each of the green vertices, or the original left vertices. Okay, they have exactly 3 neighbors, all on the right. What you do is you add these spurious purple edges. You add these spurious purple edges so that every green vertex or the original left vertex is now trapped inside a triangle. So together with the 3 neighbors, now it forms a K4 in this new graph. Okay. Now this new graph, you subject it to a proper 4 coloring. Okay, you subject this new graph into a proper 4 coloring and do our color merger. Color merger is your color 1 and 2 will be merged into a single color. Color 3 and 4 will be merged into another single color. Then you can notice that any green vertex here, or the original left vertex in the bipartition, sees a triangle in its neighborhood, in its open neighborhood. Now this triangle, under any proper 4 coloring, will get 3 different colors at least. Hence, after merging, it will see 2 of the merged colors at least. So every green vertex is happy. It has seen both the merged colors in its neighborhood. Okay. So if you say it in terms of the previous picture, this coloring makes every left vertex happy. Every vertex on the left side is happy in the sense that it sees both the colors on the right side. Now you can repeat the same process in the opposite direction, right? This time you delete all the red edge. So the first process gives the colors. We retain all the colors for the right side vertices. Now we do a separate coloring for the left side vertices. How do we do that? We delete all the red edges, and then if any red vertex, because of the crossing condition, every vertex on the right has at least 3 neighbors on the left. If there is more than 3, we delete some of the edges so that exactly 3 edges to the crossing edges survive. You will get a similar planar graph. Maximal, make that maximal by adding these spurious purple edges so that every red vertex will then have will be trapped inside a triangle, do a proper coloring, do a color merger, and every right side vertex will also be happy. So you do this idea once to the right side, once to the left side separately, and you will end up with a 2 coupon coloring. Every vertex will see both the colors in its open neighborhood. And so this proves the case when you have a, this is just a, this proves the case when the minimum degree of the triangulation is at least 5. Okay, this is the paper by Bercy and Gabor where they solve it. And we extend, as I mentioned earlier, we extend this method. So quick recap, what are the main steps in the proof? We start with a triangulation G, which has a minimum degree at least 5. Our step 1 is to find a max cut in this graph. Max cut ensures that every vertex has at least 3 edges crossing the cut. Now you do the pruning the edges, adding extra edges to the other side so that every vertex on the left side sees a triangle, then do a proper 4 coloring and a color merger, and then repeat it on the other side. Okay. Feel free to ask me if this process is not clear. We are going to extend this process. Okay, so our contribution is that we extended this process so that we could also work with degree 3 and degree 4 vertices. Note that since we are working with a triangulation on at least 4 vertices, we will not have the case when of degree 2 or degree 1 vertices. The minimum degree is going to be 3. So we only have to handle the 3 degree and 4 degree cases separately. Okay. So the key idea is that instead of taking a full max cut, we do take a special kind of max cut, or in another words, we try to protect the 3 degree and 4 degree vertices so that we do something very counterintuitive. Earlier, we wanted maximum number of neighbors of any vertex to be on the opposite side. But for 3 and 4 degree vertices, we will try to do the counterintuitive thing. We will try to retain their neighbors on their own side. Okay. We'll start by seeing how we do that for 3 degree vertices. Okay. So suppose you have a 3 degree vertex. What we do is, let's to keep the discussion simple, let's imagine there is only one 3 degree vertex on once in the graph. Okay, to keep it simple. Now this 3 degree vertex will have its 3 edges incident on it. We call these 3 edges as protected edges. Okay, this is what is highlighted in this picture in blue. Okay, so the edges that are incident on a 3 degree vertex, we call them protected, and the endpoints of the protected edges, we call them protected vertices. Okay, this is just a terminology. We haven't done anything. But now the key idea is here. Okay, the key idea is that when we take a max cut, this time we do not take the the unconstrained max cut. To the max cut, we add this extra restriction that no protected edge crosses the cut. Okay, so which means any of these edges that we highlighted, which are nothing but edges which are incident to these are edges which are incident to 3 degree vertices, right? They there's a slight delay in my tablet refreshing. Yeah. So what I was saying is that none of the protected edges cross the cut. So so again, I'm not talking about an algorithm here. We can think about how to implement this as an algorithm also by actually contracting this K4 into, or contracting every protected edge into a single vertex, and then running a max cut algorithm on the planar graphs if we need so. But at this point, let's not think about the algorithmic question. There exists a max cut where with the extra restriction that the protected edges do not cross the cut. Okay. So now, what is the guarantee now? Now, for the endpoints of protected edges, we do not have that original guarantee that at least 3 neighbors will be on the other side. But for all the unprotected vertices which do not end up at the endpoints of protected edges, the earlier argument works. At least half of their neighbors will be on the opposite side, because if not, we can switch the location of that vertex itself. Since that vertex is not incident on any protected edge, this shifting is legal. The shifting is not going to make any protected edge cross the cut. Okay, so this is still okay for all the unprotected vertices. We have the earlier claim, right? Now we mimic the same process that we did earlier. We prune one side of the graph, in the sense we delete all the green edges and green edges, and then if an unprotected vertex has more than 3 neighbors on the opposite side, on the right side, you retain exactly 3, remove the others. Then you add those extra purple edges so that these 3 neighbors then form a triangle on the red side or the opposite side. Do a forecoloring of this, proper forecoloring of this graph, do a color merger, and what you end up getting is that every unprotected vertex on the left side will see both the merged colors on the right side. You do the same process in the opposite direction. Now, if you do the same, I'm really sorry for the network issue here. It suddenly started raining very heavily here. No. So you do the same process on the other side. I think I'll wind up in 3 minutes. So this takes care of the unprotected vertex on the right side. Now, the key contribution from, or the key next step is to see what to do about the protected vertices, or the protected means the 3-degree vertices. In this case, protected means the 3-degree vertices and its neighbors. Okay. But for that, if you see, we actually do not have to do anything, somehow we are very lucky, right? All the protected vertices will end up seeing the two colors from its own side. Okay. Why is that? Because look at what happens to a protected vertex. When you are trying to help the vertices on the other side, we can make its neighborhood, complete its neighborhood into a triangle, because we are free to add all those extra edges here, right? So since we are free to make them into a K4, this vertex, this 3-degree vertex actually sees. In fact, sorry, I think I made us. I should say that maybe I'll use a different color to highlight this. The 3-degree vertex, it's those 3 neighbors. Among them, the edges, I can actually, those are the original edges, that are not as spurious edges. So you, in some sense, have a complete graph on 4 vertices. A K4 there, in a proper coloring, the K4 will get 4 different colors. And so when you do a color merger, in fact, all these 4 vertices are happy. So the 3-degree vertex and all its neighbors are happy. Whereby happy, I mean they see both the merged colors in their neighborhood. Okay. So this is the idea with which we can make all the 3-degree vertices also happy. In the interest of time, I will skip the how to handle 4-degree vertices is a slightly more complicated case, but in the interest of time, I will skip the 4-degree part. And this is, this kind of winds up the talk. What I skipped is the detail of how to handle the 4-degree vertices. And when you have multiple such vertices, you have to work with a maximal independent set among the 3 and 4-degree vertices. But that's more of a technical detail. The key idea is in keeping some of these edges protected. Okay. So I think, sorry for exceeding the time, I guess. So with that, I conclude the talk. I'll be happy if there are questions.
Okay, thank you so much, Professor Deepak, for your nice presentation. Is there any questions, remarks? Actually, Deepak, this is the first time that I see that there is a connection between coloring and the parameter domatic, total domatic number. Very nice, very nice relation. And another thing about your coloring, Copenhagen coloring, is there any method to count the number of K-couple coloring of a graph with, for example, K colors? I think this is a difficult question.
Correct. It's a difficult question. It would surely be exponential even on like small graphs, but it's a very, very interesting question. In fact, maybe one starting point would be to study uniquely K-coupon colorable graphs, graphs where you only have one way to do them, except for the fact that you can flip the colors. I think there is some work on that, especially when in the context of regular graphs. I do not remember the
Okay.
exact reference, but I had stumbled upon one such book.
Okay. Thank you so much. If there is no question, let's thank Professor Deepak for his nice presentation. Thank you,
Thank you.
Deepak. I hope to see you in person
Sure.
in a
As I
conference
told,
class.
yeah, it will be wonderful.
Okay. Thank
Thank
you
you
so
for
much.
the opportunity once more.
Okay. Oh, okay. I think Hamid, we have a 4 or 8 minutes break to the next
Okay,
presentation.
okay. Let me thanks Professor Deepak for
Thank you.
the nice presentation. As I hope so much to meet you in the future in person in Novosibirsk.
Sure.
And
That'll be
I
wonderful.
wish you success in your research.
Thank you. Same to you.
Thanks again.